Hi everyone, this is the second part of size and Venn diagram. In this part, we're going to look at how to use a Venn diagram to solve some application problems. First of all, a Venn diagram is just a tool to help us understand the relationship among the sets. Basically, the components of a Venn diagram is that you're going to have a rectangle first, and that rectangle represents the universal set. And then for other individual sets, you're going to use the circles. So each circle represents a individual set. Now, you could have two sets, and you could have three sets. Say you look at these two diagrams here. One contains two circles, set A and set B, and the other one contains three. Most likely, you're not going to see three size problems in your homework problems, especially application problems. But here we just try to introduce Venn diagram in general. Then we look at examples that are more closer to your homework problems. First of all, let's look at why we draw this two sides Venn diagram the way it is. Two circles in it, partially overlapped. Why we draw it like that? Okay, first of all, we know the set operations. We learned in the first video. If you have two sides, there's about actually three scenarios about two sides. So let's take a look at that. If you have two sides, let's say A and B. There are three scenarios that relate these two sides. Either these two sides have no common elements. So they have no common elements. That means in terms of graph, they don't intersect because there's no common elements. It goes like this. You draw it like this inside rectangle. Let's say this is set A, this is set B. And another scenario is that these two sides are partially overlapped, the two circles, which indicates that there are some elements that are common. There's some common elements. So we can draw it this way. Set A, set B. So this part indicate the common element. We use A in the section B, right? We learned this before. That's the meaning of intersection set. You have some common elements between the two sides, indicated by this common area, which is intersection between two sides. Or you could have third scenario. Set A is a subset of set B. That means everything in A is also in B. Let's say this is B, and this is A. So everything in A is automatically in B. So A is a subset of set B. That's three possible scenarios. Or you could have everything in B is also in A, so that the B circle is inside A circle, but that's the same kind of scenario. So basically, in terms of relation between two circles, we only have the three. And actually, all of the three circles can be represented in one drawing. That is this. In other words, this can represent all of the three scenarios. But why is that? Now let's look at the reasoning. In this case, there's no elements that are common, right? That means in the section set going to be an empty set. So this portion represent the intersection set. If there's no element in this shaded area, that means it is equivalent to this, even though we draw it this way, but here it's empty, there's no elements in it. That still indicate that these two sides are, they don't have anything common, that which is this. And this drawing can also represent this scenario. So in case it is this scenario, think about that. If all of the elements of A are in this area, that means everything A is also in B. This drawing can also represent this scenario. It depends on where you put those elements. So in other words, this partially overlapped circles, two circles partially overlap, can be used to represent all of the three scenarios. In other words, whenever we deal with two sides Venn diagrams, we always draw it this way: two circles inside a rectangle, which is this. So we always draw it this way whenever we deal with two sides Venn diagram. And this is a three sides Venn diagram, and we have these three circles interact this way, and which goes like this. That's how you draw that in case you need to draw three sides. This is the universal side. Usually we use a U to label that. Then first you draw two circles this way. We already mentioned that. The third circle will overlap with all of these two, including this area. So if this is set A, set B, set C. So that's a standard way to draw a three-set Venn diagram. Okay, let's move on to the next slide. Now let's look at this first topic, which is if you are given a Venn diagram such as this one, how to answer some questions using this Venn diagram. So first, let's look at this how we basically translate this given size into a Venn diagram. First, we have universal set, which has 1 through 10, two individual sides, A and B. Notice that we have a common element between A and B, which is say 3 and 4, right? 3 and 4. So look at how we draw that. 3 and 4 is in common area between A and B. So this part represents common area. That's why I put a 3 and 4 in here. Besides 3 and 4, side A also contains 1 and 2. That's why it's 1 and 2 also inside circle A. So 1, 2, 3, 4, they're all inside circle A. But 3, 4, since it is shared with B side, we put it in this shared region. Same thing for side B. We have 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. But among all of these elements, 3 and 4 are in the intersection portion of these two sides. That's why 3 and 4 is in this area. That's how we represent size using Venn diagram. Now let's look at, this is an example that we can answer some questions for the Venn diagram. And look at this example, given a Venn diagram, answer questions. In this particular Venn diagram, each number represents how many elements in that region. So these numbers actually is not the members in those sides. It represents the number of members in those sides. So be very careful when you do homework. Always read the description to understand the meaning of these numbers in here. Now, we have a 3 sides Venn diagram, and this 3 sides has actually different regions. Later on, when we create Venn diagrams, we're going to talk in detail about different regions in the Venn diagram. But for now, let's try to answer these questions one by one. How many elements in set B? So set B is represented by the circle B, right? So how many elements? We're going to add them together. 1 in this region, 7 in this region, 3 in this region, 6 in this region. They all belong to set B. So 7 plus 3 is 10, 10 plus 1 plus 6 is 17. So we should have 17 elements in set B. So this is straightforward. Now, how many elements in set A? Basically, this is the same question, just a different set, right? So we add all of this number of elements in different regions together because they all belong to set A. So this is a 7, another 7, that's 14, 15. So 15. Add them all together. Just remember, for this particular example, those numbers represent how many elements in those regions. Now, question number 3. I just copied that Venn diagram in here, so they're exactly the same thing. How many elements are in A but not in C? That's interesting. In A but not in C. Since we are given this Venn diagram, actually very easy to read the answer. But here, before we look at this Venn diagram, I'd like to present the way to represent this statement in terms of sets. So we want elements in A, this A. At the same time, we don't want those that are in. So at the same time means like and. And I remember in the last video, we mentioned that in the section can also be represented by the word and, right? It's like in the section. In the section with what? We don't want anything in C. This is in C. We don't want anything in C. So that's the way to represent it using a set notation. Now, in terms of answering the question, it's much easier. Look at those elements in A, but not in C. So here, all of this is in A, but we don't want those that are in C. Which one in C? 2 and 7 in C. The 9 elements in C. We don't want that. This is C. So we only want this 2. This 2 are still in A, so that's a 6. You can see that in the end. The answer is 6. Now, next one. How many elements belong to A or C? Now, I need to say something about this or. We mentioned that we can write in the section set using word and, right? A and B. How about union set? We can use the word or to represent the union set. So these two are equivalent, exchangeable. Since they ask us or, it is equivalent to they ask us A, set A, union set C. In other words, we want everything in circle A or circle C. A or C. How many? Let's count. This is 5, 6, 8, 15, 18, 28. So add them all together because that is like a joined side between A and C because union means joined side. So the 28 is answer. There are 28 elements in these two circles. So this way is straightforward as long as we understand the meaning of this or. Now question number 5. Question number 5. How many elements belong to set A and set B? Oh, I guess most people can answer this question now. And is equivalent to intersection. Between A and B, this intersection between A and B, this area, set A, set B. So 1 plus 7. And that is 8 elements. That's 8 elements. Now question number 6. How many elements belong to set B and set C? Set B and set C. So that's in the section, right? And it means, oh, there's another one. Oh, yeah, I see it. Okay, let's read that. How many elements belong to set B and set C, but not to set A. It goes like this: belong to set B and set C. At the same time, we want elements in B and C at the same time. And means at the same time intersection, but not A. We don't want A. Whenever you don't want something, use the intersection with complement of that thing. So this is representation. You are not required to write something like this, but this is representation using sets is equal to you read it from here. So we want those that belong to both B and C, but not belong to A. Belong to both B and C. That's here. Belong to both B and C, but not A. This is A. We want that. So answer is 3. Answer is 3. The answer is 3. So you don't need to worry about this as long as you under the meaning of this statement. The answer is 3. Okay, question number 7. Similar to question number 6. How many elements belong to set A or set C? A or C as a union, but not to set B. Belong to any of this is okay, joint set A and C. I don't want B. I don't want anything in B. So let's say can be in C or A. So A or C. Here's the whole thing. Can be in here as long as it's not in B. So for this whole thing, which part in B? This is in B, this is in B, this is in B. We don't want that. So in the end, we only have 5 plus 2, 7, 7 plus 10. That's a 17. So that's a 17. Yeah, this is just the explanations. I already did that. So next one. Here's the second type of questions here. We are going to use a Venn diagram to solve application problem. The general process is that once you have a problem, especially a survey problem, you're going to create a Venn diagram first, and then you need to populate different regions in that Venn diagram with your data. And then after you have that, you are ready to answer any questions. The reason is your diagram is a complete representation of the description of your problem. That means anything that is reasonable can be asked and will be part of your Venn diagram. That means you can answer any questions. So let's demonstrate this whole process using Venn diagram to answer solve application problem. Now, here is a description, as an example. Yeah. Let's do it this way. The results of a survey of 50 students indicate that 30 like red jelly beans, 29 like green jelly beans, and 17 like both red and green jelly beans. How many of the students surveyed like only red jelly beans? When they say 30 like red jelly beans, that include anyone who like red jelly beans, including those who like both. Now the question is, how many students only like red jelly beans? They don't like both. This kind of question first is this one is relatively easy to answer even without creating a Venn diagram. But I strongly suggest that you learn this whole process, create a Venn diagram, populate different regions with your data, and answer questions. And the reason for that is once you have a little bit more complex problem, there's no way to answer questions without a Venn diagram. That's why we learn how to draw a Venn diagram. So now here's how to do that. First of all, you have a rectangle to represent the universal set. So I just draw this rectangle and label it universal. You can put it in any corner, doesn't matter. But now we need to determine this U represents the whole thing. Whole thing we have 50 students, right? They surveyed 50 students. Now we want to determine how many circles we should have. Remember, we could have 2 circles, one diagram. We could have 3 circles, one diagram. So how many circles should we have? Each circle represents a universal individual set. So in other words, the question is how many sets we have here. Now, if you read it, we have 50 students. When they answer this question, which jelly bean, which kind of jelly bean do you like? Basically, there's 2 different kinds of jelly beans. One is red, one is green. We'll separate these 50 students into different groups. For example, some people only like red ones. Some people only like green ones. Some people may like both, right? Other people may like neither of this, right? So basically, there's 2 different colors of jelly beans separate this whole group of people, 50, into 4 different possible groups. Like only 1, 2 different groups, right? And green, like both, that's a 3rd group. Like neither, that's a 4th group. So basically, there's 2 sides separate this whole group of people, 50, into 4 different groups, subgroups. So this is 2 different jelly beans is our 2 circles. Okay, now since we decided we use 2 circles, this is a standard way to draw that. And one is a red one is green one. Now after that, we need to label each distinct regions to represent different group of subgroups of people. People who only like red, which is here, right? People who like both, that's here. Who only like green, that's this area. Well, how about those who like neither of this? That will be outside both circles. It's this region, outside both circles. So we are going to label these 4 distinct regions using Roman numbers. That's just a convention. So I label this region as 1, only red. This region 2, both. And this region number 3, only green. And outside both circles, the rest of areas, region 4. There's no order, which one is 1, which one is 2, which one is 3, and 4. It's totally random. I just read it this way. Now, after you have this labeled, now you need to fill these 4 different regions with your data. Now it's time to read this again to put it in numbers. So now this is the principle to put in to populate different areas. You always do fill in the overlapped region. First, this is the super important part. You always label the overlap region first. So for 2 circles, we only have this. This one is the most overlap. If you have 3 circles, always label the most overlapped first. So in this case, we want to know how many people like both, right? So we read it 17. 17 like both. So second area has 17 students. After that, we look at the non-overlapped region. So now let's look at region 1. What number should be in this region 1? Now region 1 is part of red circle, right? Part of red circle has 17 students. And part of red circle, this is the student who like both, right? But we still have some people who only like red one. What is that? How do I do that? Now we are given that 30 students like red jelly beans. That means the whole circle, red circle is 30. but 17 of them is in here. How about the rest? Must be 30 minus 17. This whole thing, get rid of this, that's this area. So that's a 13. So that means for this region 1, you're going to use a red circle minus second region. What is here? So now we are second step. We done second step. Now third step, we want to know what should be in region 3. The logic is very simple. It's very much the same. We use the whole circle, subtract this one. So this one going to green circle minus region 2. And the first one is 30 minus 17, right? This one, let's say how many people like green one? 29 like green one. So 29 minus 17. So this goes in here. So this is 13, this is 17, this is 12. Now, let's actually we can answer questions now, but this is a demonstration how to solve this survey problem. So I'm going to go ahead and finish this whole process. Now, how do we figure out region 4? Region 4 is that this whole thing subtract all these numbers in region 1, 2, 3, 4, because the whole thing is only 4 regions. But subtract the other 3, they got number 4 regions. So 50 minus 13 minus 17 minus 12 minus this minus this minus this. So let's say what do we get? This is 30, this is 42. We only get 8 left. So region 4 is 8. Now imagine that after you have this Venn diagram, you can answer any questions you can ask. If they ask how many people like red jelly beans, that's whole thing is right. That's 13 plus 17, that's 30. You know, that's right. If they ask how many people like green ones, add these two together. How many people like both? This. How many people like red or green? That's a unit. Add them all together to the 3 numbers. And how many people like neither of this? That's 8. So you can ask any questions. That's why we create Venn diagram first. So for this one, we already know the answer. They ask us how many students only like red beans, and that is a 13, right? That's a 13. So that's the answer. And for the next several slides, basically is the explanation about the process to create a Venn diagram and populate different region answer questions. So since I already did that, let's move on to the next example. So it's just the process how to create Venn diagram. You already know that. They label as the Roman number of different regions, populate different regions. And after you have all of these regions populated, and you can answer questions. See, that's our answer. Now let's look at our second example, and this is our last one. This one is a little bit more complex, but the whole process remains the same. Let's look at it. Uncle Lee made 578 cakes for selling last week. 397 of them were added with peanuts, and 253 of them were added with sugar. If 104 of the cakes were added with nothing, how many cakes were added with both peanuts and sugar? So now, this is a scenario. It's pretty much like the last one, and Uncle Lee had this 578 cakes in total, just like those 50 students in total, right? And then some of these cakes were added with peanuts. Some of those were added with sugar, just like some students like red wine, some students like green jelly beans, right? And some of these cakes were added with both sugars and peanuts, like those some students like both colors of jelly beans, right? So exactly same scenario. What I mean is that whenever you have survey problem, you need to determine how many circles you need inside that Venn diagram. That means how many sides we need. In this case, the additive, like either sugar or peanuts, we'll separate this 578 cakes into different groups. Some cakes has just one peanut, either peanut or sugar. That's two subgroups, right? Or has both. That's the intersection of those two sets. And some cakes have nothing added. That's a third group. So in other words, the structure of this Venn diagram is exactly the same as the previous example. The only difference is that instead of two different colors of those jelly beans, we have two different additions, edited material. One is sugar, one is peanuts. Otherwise, there's no difference. So, or Venn diagram going to be like this. First, the universal set, and we have two circles. One is added sugar, one is added peanuts, right? Yeah. Now this is region 1, region 2, region 3, and region 4. Now we just fill in numbers and answer questions. Let's fill in numbers. First, region 2, because we always do the overlap region first. Now overlap, this means this is those cakes that added with both sugar and peanuts. Do we have the number given? Actually not, because they ask us how many cakes added with both peanuts and sugar. We don't know that number. So what do? We don't know that number. That's not a big concern. Let's give it X. We're gonna solve this first. So that's X. So the goal is to fill out each regions with numbers. Then we can answer questions. Now let's say this is the overlap region. Then we do region 1, 3, and 4. There's no particular order. It doesn't matter. So let's say region 1. Region 1 apparently using this whole sugar circle, subtract X, right? Get rid of that, you get sugar only. So region 1 equals sugar circle, sugar minus X. So how many added sugar? 397. Oh, not that one. 253 added with sugar. So 253 minus X. So this region, 253 minus. So that means there are 253 minus X cakes were added only with sugar. So now let's look at the region 3. Apparently equals to peanut circle subtract X. So how many were added with peanuts? That is 397. So 397 minus X. 397 minus X. Now the last one added of that. So we are given that 104 of cakes were added with nothing. So region 4 is just a 104. We are given that 104. Now, before we can answer any question, we have to know X, right? Imagine if you have X, this number, we solve it, we know X, put X in here, and calculate these two regions. So after that, we have a number for each distinct region. Now, at that time, we can answer any questions. So currently, most important part is solve for X. Solve for X. How do we solve for X? We need equation, right? Now, one piece of information we have not used, and that is this. Total number of cakes. When we add these numbers in different regions together, it will be equal to 578. That's why we label this distinct regions, because there's no overlap for these distinct regions. Add them up, you're going to get a universal set. So let's do that. 253 minus X plus X plus 397 minus X plus 104. This will be equal to 578. Now we just need to solve this for X. Let's do that. Time to need to have this calculator. I'm gonna add the three numbers together, so all positive. So 2, actually, this x is x cancelled, right? Minus x plus x. So 253 plus 397. And then plus 104. You get 754. So 754 then minus x on this side equals 578. So solve for x, basically move x to this side to make it positive. Move this as 578. Hold on, I must have done something wrong because otherwise it's going to be a negative number. We cannot have negative number for sure. Let me see if I read anything wrong. 253 minus x and plus x, 397 minus x. That's right. Then plus 104, that is right. 578, yeah. 754. Now let me redo the calculation. Maybe I put some wrong thing. 253 plus 397 plus 104 equals 754. That is right. 754 and minus x, that's right, equals 578. I don't see anything wrong. Let me double check. 397 were added with peanuts, 253 were added with the sugar. So 253 minus x, that is this for sure. And 397 minus x, that's this part still right. And we have 578 for the whole thing, and 104 added nothing as here. Oh, still right. Must be something really weird. So we're supposed to add this 4 number together to be equal to 578. Just be careful. 253 minus x, then plus x, then plus 397 minus x, then plus 104. That will be equal to 578. Nothing's wrong. 250, this is almost 400. 650, 104. Oh, that is right. Everything is right. And somehow in my head, I read this one as 7, this 5 as 7. That's why I said, how come it's getting negative? There's no way. So 754, move this 578 back. Whenever you move any term in the equation to the other side, change the sign to the opposite. So minus 578 equals x. Let's do that. So 754 minus 578. So we get 176. So it's equal to 176. Okay, now we can put numbers in here. X is 176. 176. Now let's do the calculation here. 253 minus 176. 77. So 77 in here. And 397 minus 176 equals 221. So 221 is only peanuts. Now, how do we know, by the way, before we answer questions? Because we have to make sure these numbers are right. If this number is wrong, your answer will be wrong. So how do we know this answer is right? If you add these 4 numbers together, it has to be 578, right? The total number of cakes. So let's do that. 77, just verify, plus 176 plus 221 plus 104. 578. So everything is right. Now we are ready to answer the question. How many cakes were added with both peanuts and sugar, and that is here, right? 176. So that's the answer. And the rest is just this whole process, which I already explained, basically. Yeah. And this is our answer. And this is the end of this video. See you in the next video.